So welcome to your very first internal force problem that comes in a very specific form, as you can see here on the top of the page. In fact, it comes in a form that you won't see later ever again. So let me explain what I'm talking about. So the problem asks us to determine the internal forces, normal force, shear force, and bending moment at specific locations. And this is the only time you will see this at x equals to 3.9999999 meters, at 4.000001 meters, and then you can read the other numbers here, right? But what I'm trying to explain to you here, or what I'm trying to make clear to you here, because I sometimes see this go wrong in the classroom, is I want you to understand that you can have a 4-meter distance x here, notice the x here on the bottom, that is actually acting to the left of this force, and that would be 3.9999999. Or I can have 4 meters just to the right of the force, and that would be 4.000001. And again, no engineer right in their mind would say it like this. An engineer would probably more say it like this. But later on, we will just say at 4 meters. In fact, later on, you will just do it at every instant along the beam. So you will do it in terms of x. But for now, let's just go ahead and calculate the forces at x equals to 4 to the left of the concentrated force, at 4 to the right of the concentrated force, at 5 to the left of the concentrated force, and at 5 to the right of the concentrated force. So let's go ahead and do that. As we know from our explanation before, we need to find the support reactions first, but keep in mind that we actually already solved the problem in lecture 10. And so I already remember that my support reactions were as follows. I had a support reaction that was going up here. I had a support reaction that was going up here. And I had a support reaction that was acting in the right direction on the left side. And the numerical values here were really 43.3. And the vertical one was 11.43. And the second vertical one was 23.57. Of course, all in Newton in this case. Okay, so now I have my external forces. Now remember what I need to do. I need to go ahead and draw my free body diagram for specific cuts. I'm going to make a cut here. That's going to be the first thing I'm going to do. I make a cut here. That's the second thing I'm going to do. And then third here and fourth here. But I will do that on the next page where I prepared free body diagrams for these specific cuts. So I will see you there. All right, so now I have prepared something for you. Actually, the first 2 cuts are prepared. So let's take a look at the very first cut here on the top. And as you can see, that cut actually has a length of 3.999999 meters. And remember that the first thing I need to do is bring in my external forces. So what external forces did I have? I had a support reaction here that was pointing upwards. I have a support reaction that was acting horizontally, and they had values of 11.43 and 43.3 Newton. Now, this cut is currently not in equilibrium, so I'm going to bring in my internal forces, which are technically now external forces because I made a cut here. And the forces that I bring in is my moment. I will bring in a shear force, and I will bring in a normal force. Now, in which direction should I point them? I should point them according to my study card, and you of course have this in front of you. You have to trust me that I have this in front of me right now here as well. So my moment would go in this direction, my shear force would go in that direction, and my normal force goes in that direction. Why? Because I folded my card in half and then lined up the dashed fiber here or the reference fiber here, and then I knew in which direction I have to do that because I have a right cut here. Okay, so I should also name these. So for example, I should call this here moment at 3.9999. I'm not going to write this all out. Here I have V of 3.9999 and so on. And I have the normal force of 3.9999 and so on and so forth. Now, how do I solve this? To no surprise, very similar to solving cantilever problems, because in a cantilever problem you have the three support reactions that are unknown. So these are my three unknowns that I will solve for using the three equations now. But the only difference to a support reaction problem is that now I'm bound by the positive definition. So this is already positive defined. So if it comes out negative now, I will not flip it around. I will just leave it as such and call it a negative normal force or negative shear force, negative moment. So from now on, I call it positive or negative. I do not flip it around. So let's go ahead and calculate the sum of the forces in the x direction. 0 is equal to, I start with my unknown, plus, and I say positive n 3.99, and I use a double positive on purpose here, and plus 43.3 Newton. And therefore, my answer here for n at 3.999 is really equal to, now I have to be careful, negative, right? Negative 43.3 Newton. And yeah, you would say that, hey, negative means that my arrow now points to the left, and that is correct, but engineers have a specific meaning of the negative, and it means that the negative now puts this into compression. So an engineer would say that this now is a compression force, because the member here is actually now in compression. But this is my result for the normal force at that location, so I can double underline it. And I can move on to my shear force. Now, how do I move with my shear force? I always start with my unknown as well. So let's go ahead and understand that it's actually pointing downwards, but it's positive, right? So I use, again, two signs here. I have a positive V 3.999, but this positive defined one is actually pointing downwards, therefore it's negative. And now this is hopefully balancing the plus 11.43 Newton. And therefore I know that my shear force at 3.999 is really equal to positive 11.43 Newton. And that now will not be interpreted other than that the shear force is positive. So I don't say it's up or down. It's relative to its positive definition here. And notice that I brought in my positive definition and I found it out to be positive. So that is my shear force. Last but not least, I use my moment counterclockwise positive. And I start again with my moment here with my unknown. So plus positive defined m 3.999, and this is again, this plus here stands for, hey, I'm following this arrow in my drawing, but it now turns counterclockwise, which makes it positive. So I use a double plus, and some people wouldn't do that, but I think that gets the point better across, at least as you solve more of these problems, even though initially it confuses more, but it is more precise if you think about it. All right, so now what do I have to do? I have to rotate about this point, right? Remember when you found the moment for your support reaction of a cantilever, you took the moment about this point. And so I do the same thing here now with my 11.43 times its lever arm. So really what I would be writing here would be 11.43 Newton multiplied by 3.99999 meters. Yeah, and now in which direction does that rotate? That clearly rotates about this point in the clockwise direction. So let's make that a negative. And just to be clear, this is all negative. So therefore I know now that my moment at 3.999 is equal to positive 45.72. and that is, of course, in Newton meters. And the positive here now doesn't tell you clockwise or counterclockwise. It technically does tell you that, but we are dealing with internal forces, so we're not flipping anything around anymore. So I'll say that again. We just state either if it's a negative or a positive. And I want you to always include the positive. Do not forget the positive. Your answer for internal forces should always have a mathematical sign. Even if it's positive, you need to indicate that it's positive. And this will become more important later down the road. But this now completes our first cut for the free body that we have drawn up here. Just before I move on to the next cut, which would be to the right of the force that we cut here before. But before I move on to that, please understand that this is identical to actually solving the opposite system, which would be on the right side. So I think it looked something like this. I had a support reaction on the right side, which was called RBY, and I believe that was equal to 23.57. I also had two other forces acting. One was directly at the cut here, which was 10. And then I had a sloped force here with 50 under an angle, so 50 and 10. And if you were to make this cut here now, you would find that you have the same answers for your shear force and your normal force and your bending moment. Of course, they would point in other directions now. So for example, the shear force would go in this direction, moment would go in this direction, and the normal force would go in that direction. But this would be equivalent. And hopefully this doesn't confuse you. You may think like, how can this be equivalent? Because there's more forces acting on here. But keep in mind that here you have different support reactions than you have here. And of course, if you glue the system back together, these forces have to disappear, right? And that's something you can actually verify. And this is why this is such a nice class. When you take an exam, for example, you can be 100% certain that these answers are correct because you can verify them yourself before you turn in your answer. And so this is really a very beautiful way to look at these problems. And I believe we can use this concept now for all the following cuts. So let's move on and talk about the next one. The next one is the one down here where we're actually looking at the same system, but now we're adding a force into it because we are now to the right of this force. And so let me redraw my free body diagram here, or complete my free body diagram. So I had this force and I had a normal force, sorry, not a horizontal support reaction. This was 43.3, 11.3. And now I bring in my study card again, which of course looks exactly the same as it did before. So I had a vertical force and I have a horizontal force and a moment. And the way they are pointing would be in this direction. And now we would talk about M at 4.0001, V at 4.0001, or however many zeros you want to add there, and N at 4.0001. And what I'm really trying to tell you here, or try to make clear to you, is that you can cut just to the left of this force. That's what we did in the previous cut, or just to the right of this force. And so here we're cutting to the right. So now my equilibrium equations look slightly different, but maybe for clarity I also use proper colors this time. So I start with my normal force and I say plus N at 4.0001, and this now is actually in the positive direction, so plus. And now I need to include the 43, so plus 43.3 Newton, if you will, and that is also acting in the positive direction. So therefore we will find that our normal force actually did not change. It's in fact the same equation because there's no normal force added to the system. So we will find that my N of 4.000001 is actually equal to negative 43.3 Newton. And that is once again a result. And yes, it's the same result, but you were asked to solve it at that location, so therefore we need to underline that. All right, now up to the shear force. We start with my unknown. So this is positive defined V of 4.000001. And of course, I understand that it's actually pointing downwards, and so therefore it's negative, right? It's not positive, but it's positive defined, and that's what I tried to indicate with the purple color. Now, my red color is acting positive 11.3 Newton. And just to be uniform here, I also make that positive positive. And I now need to actually include this 10 Newton here. So therefore, I also have a positive 10 Newton because a force is always positive in a diagram, but it's acting in the negative direction. So therefore, it's going downwards. And now I can close out my equation and I can identify that my shear force at 4.000001 is equal to positive 1.43 Newton. Now that will be a result once again, so we obviously double underline that and notice that I used a positive in my answer here. Last but not least, let's go ahead and calculate the moment. So that would be positive defined m at 4.000001, which I put in parentheses, and now it's also turning counterclockwise. That makes it positive according to my definition here on the left side. So I now include my 11.3, so plus 11.3 Newton, which of course is always positive defined, multiplied by 4.000001 meters. And that has a rotational sense as well, which about this point here rotates clockwise, therefore it is negative. And then I can calculate my moment at m equals to 4.000001 meters. And surprise, surprise, it is actually the same as before, which was plus 45.72. So plus 45.72 Newton meter. It is a result, so I double underline it. And I want to talk about it real quick. You may wonder, why did I not include the 10 here? And maybe you already know the answer. It's because this 0.00001 meter is effectively 0. And so I kind of left this out. I mean, you could have added 10 times 0.000001, but you would see that it has no impact on here. And that's what I was trying to show you actually with these strange numbers that I used instead of saying 4 meter to the right. So now if you compare these two cuts on the side, you can see that there are some similarities, but also some differences. And because I cannot flip back and forth between pages here, I'm going to do it here. Usually I ask my students to do this at the end of the problem. But since we're here, let's look at it. For example, the normal force did not change, right? Why? Because the normal force did not include any additional forces between this cut and this cut. In other words, this cut and this cut in the formula was identical. Now for the shear force, that's a little bit different because here we cut just before the force that would be coming here that is actually included in this system, the 10 Newton here. We did not have that included here. But here we had it included. And therefore we actually have a difference of 10, right? So we have a difference between 11.43 and 1.43 that is equal to 10. And that difference is actually given by this force here. So the way this equation is different from this equation is indicated by that 10 here. Now for the moment, you did not really have a difference. Simply the lever arm became a tiny bit longer from 3.99999 to 4.000001. Is really no difference, and therefore the result here is actually identical. And you may think, this is not true because technically there is some difference, but from an engineering standpoint, no, there's no difference in that context. And that concludes the first cut at 4 meters to the left and to the right. And now we're going to move on to the cut at 5 meters, and we do the same thing. We cut at the left side and we cut on the right side, but I will do that on the next page. All right, similar to what we have seen on the previous page, we now have 2 cuts, one at the top and one at the bottom, that are almost identical, except here we're cutting to the left side of the force, the 50 Newton, whereas here on the bottom we cut to the right side of it. And so we get slightly different equations here than we get down here. So let's dig in and let's start with our first cut here. And as always, we have to bring in our external forces first. So let me start here with RAY, which I believe was 11.3, and my horizontal support reaction was equal to 43.3, pointing to the right. Now I want to bring in my cut. I'm cutting right here, and I therefore have to now bring in my external forces, which are technically internal forces, but I bring in my shear force, I bring in my normal force, and I bring in my moment. And of course, I need to assign proper direction according to my study card. The moment turns according to that counterclockwise. My shear force is going down and my normal force is pointing to the right. I need to assign proper names. So for example, M at technically 5. So what I'm going to do now is I'm going to call this 5 to the left. And I call this 5 to the left for the shear force as well. And for the normal force, I also call it 5 to the left, which really is equal to 4.99999. But in reality, engineers would consider that being 5. So I call that 5 to the left. All right, now we can write out our equations as always. I can go ahead and start with my horizontal force, and I start with my unknown. So plus N5 to the left. That is always a positive identifier, but it's pointing to the right. And because it's pointing to the right, therefore it is considered positive. I now use my 43.3, so plus 43.3 Newton, which is also always positive because it's in a sketch, but maybe to be unmistakably clear here, it's also pointing to the right. And therefore I can now say that my normal force in the 5 to the left location is equal to minus 43.3 Newton, which of course means that it's in compression. And now I can double underline that because it is my result, and I can move on to the next shear force. So the shear force here, I start with that unknown. Again, it's always positive, V of 5 to the left. And yeah, I understand that it's not really positive according to what you think, because it's pointing down, but I do that with my black identifiers here. In the parentheses, I always remind myself that an arrow is always positive. So now I have to identify that it's actually negative going downwards. And what's acting with it or in the same direction is the 11.3 Newton. And to be consistent, I also make that positive and put it in parentheses. But that is acting upwards, so I'm going up there. Last but not least, I have to consider the 10 Newton up here. So I also have a plus 10 Newton, which yes, it's pointing downwards, but I indicate that with my negative here to be unmistakably clear. And now I can solve this equation and find that my shear force at 5 to the left of the force is really equal to plus 1.43 Newton. Think about that. Maybe you have seen that somewhere before. I will talk more about this when I solved all of it, but maybe you can already identify why that number came out to be that way. Let's go ahead and solve the moment. So the moment, of course, again, is positive defined, 5 to the left. but it's rotating counterclockwise, therefore it's positive. And now remember that we're taking the sum of the moments about this point. In fact, I indicated this for you here, x equals to 5. So I really have to take the 11 and the 10 and rotate it about this point. Now the 10 actually does have a lever arm, but we'll come to that in a second. Let's first start with the 11.3 Newton multiplied by, what's the lever arm? 5 meters, right? Or 4.999. So 4.99999, which is really 5 meters. Put this in parentheses or brackets and give it a rotational sense, which in this case is really clockwise. Therefore, we'll make that negative. Now we also have to consider the 10 Newton in this case. So 10 Newton multiplied by 0.9999999 meters. And that also needs a rotational sense. In this case, it rotates about this point, which then means counterclockwise rotation. Therefore, it's positive. And now I can solve for my moment at 5 to the left, which comes out to be equal to 47.15. So plus 47.15 Newton meter. And by the way, remember that the positive and the negative for a moment also have a specific meaning, just like the positive or the negative have a meaning for the normal force, negative meaning compression, positive meaning tension. The positive moment means the beam is smiling, right? It has tension in the reference fiber, whereas a negative moment would mean compression in the reference fiber. And since here you have a simply supported beam where all the forces come from the top, the beam can only smile. It has to bend downwards. And therefore, it makes perfect sense that we only get positive moments so far. But we'll talk about this again when we solved the problem completely. Now we have all the numerical answers here. Let's move on to our last cut. And that is for 5 meters to the right of the force. So once again, we cut the system right here. We bring in our forces. So first we have the external forces, which are the 11.3 and the 43.3. And because we cut right here, we now have to go ahead and bring in our external forces, which are technically internal forces, but through the cut we turned them into external forces. So that's our little trick here. So I bring in my shear force, my moment, and my normal force, and I give them proper names. So N at 5 to the right side, V at 5 to the right side, and M at 5 to the right side. And please understand that now we have a force here that acts under an angle. Let me remind you that that angle actually was 30 degrees, right? So we had an angle alpha here that was 30 degrees. So 30 degrees, we will need that in our equation later on. In fact, we need it in our first equation. So let's go ahead and write out the equation for the normal force. I start with my unknown as always. So plus N at 5 to the right is pointing to the right. Therefore, I make it positive. I now bring in my 43, so plus 43.3 Newton, which needs a direction as well, happens to be positive. And now I need to add actually this 50 Newton times the cosine of 30, right? So I have 50 Newton, multiply that by cosine of 30 to get the horizontal component, or the component that's parallel to the x-axis. And then I need to identify that this is positive in this direction, but it is negative because it points to the left. And now the system is actually in balance before this force is actually applied. So the system from here to here is in balance. In fact, if you think back how you calculated the support reaction, you know that this 43.3 is just equal to 50 times cosine 30. And so now your normal force actually goes to 0. So we can say that therefore our normal force at 5 to the right is really equal to plus minus 0. And that is a result, believe it or not. So you cannot get away with just leaving it out. You have to calculate it, and you have to mathematically prove it, and you have to double underline it. But the explanation here is that this is really the x component or parallel component. And that parallel component balances the 43.3. And that makes perfect sense, hopefully. All right, let's move on to the shear force. Again, I start with my unknown, so plus V of 5 on the right side, which is pointing downwards, therefore it's negative. And let me reiterate that this comes from here, so the black negative comes from here, whereas this positive comes from reading an arrow properly in a sketch. All right, now I bring in my 11.3, so 11.3 Newton, and that has also a sense, and that is by definition positive, but it's pointing upwards, therefore it's also positive. Now I need to indicate my 10 Newton here, so I have plus 10 Newton, but that 10 Newton is pointing down, therefore it's negative. And last but not least, I also have 50 times sine 30, so 50 sine 30, and that is positive, but it's pointing downwards, therefore negative here in my black identifier. And we can now state that this is the perpendicular component. And when I talk about these components, I mean relative to x-axis. Right? So it's relative to x-axis because that's where the reference fiber is, and that's what we need to always follow our logic. But I can solve this equation now, and I can find that my shear force V of 5 to the right now is really equal to, be careful now, it actually happens to be a negative value, and that value needs to be minus 23.57, minus 23.57 Newton. And we just leave it as a negative value because we're talking about internal forces, and later on we'd want to graph them. But for now, we understand that it's a negative value. And by the way, think about the difference between this shear force and the one that you calculated before. Where do you think that is coming from? I will give you the answer about that in a second. But before, let's find our last unknown here, which is the moment at 5 to the right. And that by definition is positive, but also it's rotating counterclockwise, therefore that is positive. Now I include my 11.3 Newton, and that is positive, of course, but it's also multiplied by 5 point something, so 5.0001, so multiplied by 5.0001 meters. And that now rotates again about this point. So this force rotates clockwise, therefore it's negative, which I need to indicate here. And I include my 10 Newton once again, 10 Newton, which is also positive, and multiply that by 1.0001 meter. And that is turning counterclockwise, if I'm not mistaken. Yeah, so I turn about this point, this force turns this way around, counterclockwise, therefore positive. And now, just to be sure here, or just so that you see it once properly, we can also say that we have the 50 Newton times the sine of 30, that gives us the perpendicular component, multiplied by 0.000001 meter. So we don't really care about this. In fact, this would be equal to 0, but if we were to include this, we would have to give it a rotational sense of, let's look at it. It would turn this way around counterclockwise, therefore positive. So plus 0, right? I mean, that makes no difference here for us, but we know now that we can calculate the moment m at 5 to the right would be equal to positive 47.15 plus 47.15 Newton meter. And that once again means positive tension on the bottom, compression on the top, or tension in the reference fiber, or smiling happy guy, right? So these are our results. Let's look at it in context. In fact, if I were you, I would now compare this page to the previous page and try to really understand what happens with the different forces. Before I talk about the whole context, let me just compare what we see on this page here. So here we had a negative force of 43.3, which really resulted from this force here. But if I compare this to the normal force down here, it goes to 0 from here to here. It becomes 0 because we now add this component, the parallel component. And again, if you think about it, this is really the component that causes the support reaction anyways, and therefore it's now in balance, and we don't need a normal force anymore to balance it. Now for the shear force, we started up here with 1.43, which if you go one page back, you will find that this is the same shear force that we had just to the right of this force. So that was 1.43 as well. But now if we look down here, it actually changed. And by how much did it change really from here to here? It changed by this amount, right? Because if you look at this equation, the only difference between this equation and this equation is really the 50 sine 30. So what you can really see is that from here to here, there's no difference because you have no force, but once you add this force, something changes, and that is reflected right here. Now look at the moment, 47.15 and 47.15, that did not change. That's really interesting, right? And that is because the moment rotates about a point. So it rotates about this point and this point. And if the points are not very far away from each other, in fact, they are not away from each other at all in a sense, but we just try to symbolize it by the 0.9999999 versus the 1.100001, that they are somewhat far away from each other, but they are not far away from each other. They are very close to each other, and that's why this value is the same as this one. However, compared to the value on the previous page, you will find that you actually have a different value and that they are so close to each other. Like here we have 47, on the previous page you have 45. That is completely random, right? So everywhere in between here, from here to here, you actually would find a different value. In fact, for you to practice, what I recommend is to probably find the internal forces at 4.5 meters, for example. That is something where we will pick up the next lecture, and we will actually find the internal forces almost everywhere along the entire beam. So you can practice that and prepare for that by calculating, for example, the internal forces at 4.5 and maybe at 2.2. It's something that you could easily do now with the knowledge that we presented to you here in this lecture, and I wish you good luck with that. One last word here before we conclude the lecture is, remember that this here is pretty much the left side of the system. We could also have released the other side, right? I could have created the system here where I cut the same part, but I now introduce actually only the force here, which is, I believe, 23.57, and then I cut right here where I will bring in now my internal forces, my shear force, my normal force, and my moment. And if I use those, then I would find the exact same answers. In fact, it's very easy to see here that this force here, this shear force, which, by the way, look, that is pointing upwards, here is pointing down, right? This force, to balance this force, must be what? minus 23. And look what we found here, minus 23.57. So that clarifies that this side is identical to that one. Why did I show you this? Because in an exam, after I really studied these problems in depth, I would definitely use this cut and not this cut if I were to solve the problem. But here, this was an educational example, so we tried to show you extensively why and how we calculate these numbers. Later on, when you're more proficient at it and after you have some practice, hopefully you can find shortcuts. For example, cut the right side instead of the left side when you are asked to find internal forces at a specific location. But for now, I believe this concludes our first introduction to internal forces. We have seen how to calculate them for a simply supported beam that only carries concentrated forces. Later on, of course, we will include distributed forces, and we also will take it further to analyze the forces really everywhere along the beam. We will graph it later. But for now, I highly recommend that you explore this through your homework and really study how to find internal forces at a specific location so that you are ready to understand the following concepts, because we will really move fast forward from here on. And the topics will not become simpler, they will get more involved, and everything will rely on what we talked about today. But I believe this lecture is a very important one, hand in hand with the one where you learned how to calculate support reaction for a cantilever, because it's so similar to what we're doing here. And so if you understand those two lectures, you are very prepared for what's coming up. Just go ahead and solve the homework, but we will talk about this now after we concluded the lecture on the following page.